Dear colleagues, my name is Krasimira Ivanova. I am from the University of Telecommunications in Post in Sofia, Bulgaria. The title of my presentation is NLA Layer, a new data structure for storing of dynamic data. The presentation consists of an introduction, theoretical foundations, natural language addressing, or NLA, resource description framework, NLA layer, experiments, NLA trace system, and a conclusion. An important feature of big data is the dynamics with which the data enters the registration and processing system. In the classical version of a relational database, the time from resetting the indexes of the database is usually longer than the time of receipt of the dynamic data. Let us recall that the extremely large and dynamic data traffic requires frequent re-indexing of traditional databases. This leads at least to the loss sometimes of essential data. An alternative that allows synchronous storage and processing of large volumes of semi-structured dynamic data is proposed in this article. A new data structure called NLA layer is proposed. It makes possible to store a practically unlimited amount of streaming data with the data ready for retrieval and processing immediately after storage. Experiments have shown that NLA layer allows for the construction of big databases with constant time complexity O of 1. To avoid indexing and ensure consistent high-speed storage and immediate direct access to the data, a technology called natural language addressing has been proposed. The idea is simple: to use the codes of the letters as coordinates or addresses to access the data. For example, let's assume we want to store data for a vehicle with the number P3546 and own a dipped water Ltd. In normal indexing, the key, which is P3546, would correspond, for example, to the address 0504360, and the index pair key and address points to the first byte of the text Deepwater Ltd in a file. To access the data, we first have to find the key P3546 in the index, and then to access the address 05044360 in the file to read the contents of the record. To humans, in natural language addressing, this address will be shown as key P3546, but for the computer it will be in machine code. We replace the real index couple with a virtual one. This technology is implemented in the MD-NDB system, or multi-domain number database. It has been used in many practical solutions since the 1990s. MD-NDB is a multimodal database that works with distributed multidimensional databases, in particular RDF graphs. The W3C's Resource Description Framework, or RDF, is a standard syntax for semantic web annotations and language that allows the processing of unstructured or semi-structured data. The basic structure of RDF is a triple, which consists of a subject, relation, and object. The set of RDF triplets is called an RDF graph. In the previous article, the term NLA bit was defined as a structure set of all RDF instances with the same subject. NLA bit is a convenient construction for working with objects with many characteristics that dynamically change. Such are, for example, the documents in a documentary database. However, there are many practical tasks in which many objects have the same connection that characterizes them. For example, all cars that have gone through a toll check for a certain period of time. A set of RDA triplets having the same relation is called an NLA layer. By definition, each NLA layer is assumed to have an unlimited number of subjects and related objects, and there is no limit in the number of NLA layers. The physical organization of an NLA layer is through multidimensional information spaces. This organization maintains time complexity O of 1. The NLA layers are illustrated on this slide. Vertical arrows represent the NLA bits or subjects, for instance, the vehicle ID, and horizontal arrows represent the NLA layers or relations, for example, the toll numbers. Only values of this object, which is the time, are stored in the database presented by the green points. The storage of moving objects tracking data is chosen as the basis for the experiment in this article. This type of data comes, for example, from toll collection systems, which should allow convenient methods of payment and control without slowing down the free movement of the motor vehicles. Another example is the air traffic tracking systems. At the same time, it's a basic principle that's followed, and it's not reasonable to go through with the design and implementation of a new system, provided there is already an implemented and functioning one. It is more appropriate to look to expand its capabilities with new features. Therefore, in the present work, a functional extension is proposed, providing a qualitatively new type of data storage organization. As an example, here we will outline a distributed NLA trace system for storing data for vehicles on highways and first-class roads in Bulgaria. It's based on NLA and the NL access method and the MD-NDB. The main idea for NLA trace storage is through RDF triples like vehicle ID, toll number, and time, where all three elements are natural language strings. Toll numbers and vehicle identifiers are not recorded in the archives. They are natural language addresses. Only the time should be stored in appropriate containers located at addresses indicated by the vehicle identifiers in layers indicated by the toll numbers. It is assumed that all possible data points in an archive's hyperspace exist but are empty. This way, there are only two NL trace functions, update and read. Tests assumed that vehicles are monitored along certain routes. Some vehicles are allowed to have more than one pass through a toll checkpoint at different times, as well as several vehicles to pass a toll checkpoint at the same time, but in different lanes, meaning all the time they will be in different positions on the road and different cameras will be registering them. So several different data will be received at the same time and the system will have to store them at the same time. To perform experiments in NLA trace, two data sets were prepared, containing 1,000 and 10,000 instances respectively, which contain of triples, vehicle identifier, toll number, and time, generated at random. A fragment of the input stream is shown in the slide's left column. A fragment of the archived layers, which correspond to the input fragment shown in the left column, is presented in the right column. It is important to note that only the objects, the time values, are stored in the archive, i.e. Values marked in bold. The other data, subject and relation, respectively vehicle identifier and toll number, are natural language addresses which are coordinates of the time values. This way, a SPARQL query, for instance toll 350, may be resolved immediately at any time. The result, which corresponds to a query, is shown on this slide. The tests performed on a laptop Sony Vaio VGN have shown a recording speed of one instance from 3.1 to 7.4 milliseconds because of the time taken for the initial creation of the archival structures. The storing speed varies from 240 to about 420 instances per second. The reading speed is constant at about 2.1 to 2.7 milliseconds, meaning 600 to 900 instances per second. The speeds do not depend on the volume of data, and this approach supports constant time complexity of O of 1. Thank you for your attention.